Okay, so as I mentioned at the beginning of today's lecture, um, we're moving into the concept exploration phase, and part of the concept exploration phase requires you to build some models that will be capable of representing the behavior of your systems. So there are multiple ways in which you can create models. You can use computers. You can use physical models. Uh, Today we're going to cover a different type of model, again representing the behavior of your system, and we're going to rely on math theory, set theory to develop those models. So hopefully you have an idea of what a set is. If not, we're going to discuss the details this morning. And then we're going to see how, using this information and this theory, we can build functions for representing a specific situation. And then those functions can also help us to build a more detailed systems that involve the whole inputs and outputs that your system must generate. So let's start. So the topic again is set theory. This is the foundation for the models that we are going to start building for our systems. So here's some notation that is needed for us to manage this topic. If you're not familiar with it, we can discuss what they mean. So we can start from the top on that left side. We have the symbol representing a member or not a member of a set. We also have the empty set symbol. We have the symbols that represent such that or given that. So that's when you have a condition that is present when you're going to elaborate on a function. The Cartesian product, this you should know, equal or not equal to. A superset, and we're going to see when that applies, which is equal. So this line below it, it's equal or strict. And also we have a subset, meaning that you have defined a set with certain members, and then you can create a smaller set from that group. So it's a subset. From stat, you know that this means intersection, well, the other way around, this is union, and this is intersection. This symbol right here represents that there exists or there does not exist something that satisfies that condition. This symbol represents for all, so that means that all the members in that set are taken into account. The arrow represents implies that, so this is basically saying that if you see this, then that implies something. The cardinality, if you have a set with 3 members, basically cardinality means 3. It looks at the size of your set. R or double R represent the set of real numbers. Double Z represent the set of integers. Double F represent the set of functions. These arrows are used to represent if and only if. That is when you're stating a condition. So this is true if and only if this is satisfied. These are used in computer science to represent and or. And I think we have this one twice. So there's this and there's no, does not exist. So we're going to use this notation to represent or to develop the functions. Excuse me. You can use a computer, but you cannot print because you're going to interrupt my class.
Can I just finish that? I was told that because I was free.
Yeah, but when we have a class, you cannot do that. I think we discussed that at some point in the semester. So, okay, so let's go from there. A setup is a collection of distinct unique elements, and we shall denote a collection of elements by. Let's see some examples. So we use that collection, or we represent that collection of elements by using this parenthesis. So anything that is are the elements of the set. I can show you some examples. Very simple example. So I can name this set A, and the elements within it can be numbers 1, 2, 3, 5, 2, 1, and 10. Can you tell me if that is a set or not? Just by looking at the definition. No, because they have. Sorry. No, because it has a number that is repeated, right? So definition says that in a set, it is a collection of distinct unique elements. So if you see that there's an element that is repeated, then that means that that is not a set. It doesn't satisfy the definition of a set. So this is not a set. Another example. This is 1, 2, 3, 5, 10. In this case, we do have a set because each element inside the parenthesis is different. Okay, so this is a set. A set also can be stated in terms of terms, like for instance, colors. So we can say yellow, green, red, yellow, which in this case again is not a set because we have some elements that are repeated, and then D, red, yellow, and green, this is a set. Okay, so it's not limited to numbers. It could be terms that you can define as part of your set. The idea here is that you identify which one is a set or which one is not a set. In this case, we have two that they are set because there are elements in them that they are not repeated. Questions? Okay. When we don't have a set, for instance, like in case for A and C, if they are not a set, the name that we give them are a bag. So instead of a set, those are called a bag. A partition on a set is a collection P of distinct joints or disjoint subsets of A whose union is the actual or the original set A. Okay, so for a collection BI, where I can go from 1 to up to n, those are the number of partitions of that set. We know that BI is going to be a subset of that set, so it's a portion of that set. The intersection of any two partitions is the null set, meaning that they don't overlap. And for any member of one of those partitions, let's say A, there's that X is also going to be a member of one of the partitions. So if you're part of the larger set, that element is also part of one of the subsets. So for example, we have, let's say, let me call A the the larger set, 1, 2, 3, 5, and 10. And I'm going to start listing some of the partitions. So B1 is going to be 1, 2. B2 can be 5 and 10. B3 could be 3. And we know that the union of these three, union of B1, B2 with B3, is going to be equal to A, right? Because each one of them, they are partition of this set, and when you put them together, then we end up with this original set. Okay, so that's an example of a partition. We know that the intersection of B1 with B2 equals the null set. The intersection of B1 with B3 is also null because they don't overlap. And the intersection between 2 and 3 is also null. So, therefore, B1, B2, and B3 are partitions of A. So in systems engineering, we deal with partition as part of our description of the requirements and also as part of the description of the functions for our system. Another type of set that is very important is called the power set. And a power set of set A is denoted by this double P of A. It's the set of all sets that are subsets of this big set A, which is our original set. It is a set such that each element of A, the element X in A, is part of the power set. If and only if it is also part of the power set of A. So it is a set that each element of A is part of the power set of A if and only if that condition is satisfied. So these are the three conditions. A0 is equal to the null set. So the power of that set A0 is going to be equal to A0, which is also equal to the null set. So A0 has 0 elements, but the power set of A0 has 1 element, which is the null set, meaning that that set is empty. If A1 equals this little a, then the power set of A1 is going to be this null set plus that element A. If A2 is equal to A and B, then the power set of A2 is going to be equal to the null set plus those elements separately plus that element, which is the combination of the two. Okay, so the power set includes the null set and all the possible combinations of the elements that are part of that original set. So one question for you: if we have AN, which is a set of with n elements, then how many elements are part of the power set of AN? So if you have a set that has n elements, and you have seen what's happening with the other three examples, how many elements do you think this set AN with n elements will have in terms of its power set? If you remember your statistics class, then that will be equal to 2 to the power of n. So in systems engineering, we use power set a lot. For example, the power set of a system inputs provide an upper bound of the test sequences to test the system exhaustively. Meaning that, remember, part of our discussion on concept exploration was that we need to take into account the different conditions, different environments, So we can generate a set of inputs that will represent those environments. And knowing the power set, we can have the total number of combinations of those inputs that we have to use in order to test our system. So that's the power set. You're familiar with this one, the Cartesian product first. Another ordered pair is x, y. If x is part of A and y is part of B, then a Cartesian product of A cross B is a set of all possible ordered pairs of A and B. Should be T. So that will be equal to the cross product of A and B is going to be equal to the elements such that A is part of A and B is part of B. It is defined as follows. So that will be equal to the empty set if any of these two sets are empty, and it's going to be equal to x equals AB if we have elements A in A and B in B. Another M tuple is defined as the multiplication of all these sets from A1 to cross A2 and so on. So an example representing this Cartesian product can be the following. So we have set A, which is equal to 1, 2, and 3, and set B equal to 4 and 5. Then the Cartesian product of A and B is going to be equal to the possible pairs that we can generate with those combinations. So in this case, that would be 1, 4, 1, 5, 2, 4, 2, 3, 3, 4, and 3, 5. The Cartesian product of B and A is going to be different in the sense of the location of those elements. So if we do B cross A, that Cartesian product is going to be equal to 4, 1, 4, 2, 4, 3, 5, 1, 5, 2, and 5, 3. So as you can see, the Cartesian product of A cross B is not equal to the Cartesian product of B cross A. Okay, because those are the location of the elements is not the same. So what is the cardinality of A? So if I ask you what is the cardinality of A, can you tell me what that is? From our definition here, the cardinality of is the size of the set. So what will be the size of A? 3. What will be the size of B? 2, correct? So if you know the cardinality of A and you know the cardinality of B, then you can compute what will be the size of the Cartesian product. That would be the multiplication of the cardinality of A times the cardinality of B. So in this case, that will be equal to 6 elements. And as you can see, for both cases, the cardinality of this Cartesian product is 6, and the number of elements for this Cartesian product is also 6. So that's helpful in terms of you making sure that you have the exact number of elements that you should have for these operations. Any questions? You'll see how this connects with what we are trying to do as part of our class. For instance, when you are developing a system, you can think about the inputs of what inputs that system is going to receive. You can also think about the states of your system. So if you think about a very simple machine, that machine can have, in very simple case, can have two states, busy and idle. So those states can be changing according to the inputs that you are going to be receiving. So if you have an input that says a part has arrived and your machine is idle, then that input is going to change the state of your machine to busy, because you're going to start processing that part. So the idea with these sets or these Cartesian products is that you can represent that behavior, that if you receive this input and you are in this state, tell me what are the possible combinations of changes in state that can happen in your machine, for instance. So we are headed into that direction. Relations is very important. A unary relation on a set A relates elements of A to itself and is a subset R of the Cartesian product of A cross A. That relation, or those relations, are going to be a subset of that Cartesian product. These relations, or R, is usually described by a predicate that defines the relation in terms of these symbols: less than or equal to, less than, equal to, greater to, or greater or equal to. A binary relation is a relation R that relates elements of A to elements of B and is a subset of the Cartesian product A cross B, and it's also a subset of that Cartesian product. The domain of R, or the domain of this relation, is defined as follows. So it's going to be those elements X that are part of A and XY that are part of this relation or that Cartesian product for some Y in B. The domain and the range, they're different. The range of R, or RAN, is defined as the Y's that are part of B and are part of this relation for some X in A. So if you remember your algebra course, you remember when we defined the domain and the range. Basically, the domain are the possible values of X, and the range are going to be, when you evaluate that X into your function, what will be the value of the function. So it's the same idea. So an example, let me just write it here. So for example, we let R, is that, okay, I have space here. So let R be a relation from A to B where A is equal to 1, 3, 5, and 7, and B equals 1, 3, and 5. And this is defined, which is defined by this: X being less than Y. Okay, so that's the problem. So we want to write R as a set of ordered pairs. Okay, so want us to write R as a set of ordered pairs. So that R is going to be again a relation where we have elements X and Y which are part of, X are part of, given that X is part of A and Y is part of B, and we know that that relation that we are looking for is X being less than Y. So if that's the condition, then I'm going to look at the elements from A, and I'm going to compare each one of these elements to B, to the elements of B. And I'm going to start listing those combinations that are satisfying this condition. So in this case, those combinations are the following. We have 1, 3. So I'm going to list that set as follows. We have 1, 5, and we have 3, 5. Okay? So again, you look at the elements of A. 1 is less than 3. 1 is less than 5. So we have those elements of those combinations here. Then I move to 3. 3 is less than 5. So I list that one here. If I move forward, 5, there's no elements in B that are less than 5 or that are greater than 5. So I can make this condition true. So that's why I stop at that point. There's no other combination that will satisfy this relation. Okay, so if I were, for example, planning my production for next week, and I have these orders, but I have my production planning defined in terms of these products, then I want to see when I can produce these products by looking at my schedule. Then these are the possible combinations for make that happen. That could be an example. So I cannot produce products 5 and 7 because for me to be able to do that, I need at least this much material. That could be the case. So that's an example. So relations are used in this defining a hierarchy of requirements. So I can make that note here. Relations are used in defining a hierarchy of requirements. For instance, decompose of, incorporate, tracing requirements to functions. or binary relations of systems, subsystems, components, and etc. Okay, so relations are used in defining a hierarchy of requirements, which can be decomposed of or incorporate, and allow us to trace requirements to functions by binary relations of systems, subsystems, component, and up to the part level. Okay, so again, relations are used in defining a hierarchy of requirements, decompose of, incorporate, tracing requirements into functions. A binary relation is a relation R that relates elements of A to elements of B, and is a subset of this cross product. These relations are going to be a subset of the Cartesian product of A and B. And as I mentioned, the domain of this relation is going to be defined as this set of elements in X, and the range is going to be defined as these elements Y that are part of that set. Okay, so in terms of another type of set, which is where we are heading in terms of our definition of a model, the dynamic behavior of systems is modeled by means of functions. So for us to get to this part, we needed to understand some of the here behind sets and behind relations and behind the cross or the Cartesian products. So we now have a good understanding, hopefully, of sets and relations. So using that knowledge, we can build functions, which again are going to be the elements that we are going to use to represent the behavior of our systems. So if we have two empty sets, A and B, then we say that function A to B is a function that maps every element of A, which is the domain, to one and only one element of B, which is going to be the range. If these two elements, A and B, are part of the function, then B is the image of the element A under that function. Okay, so a function f from A to B is a relation such that A, the domain of that function, is equal to A, and that is f is defined for every element of A, which A which means that those elements are part of A, and 2, there exists A and B where B in B, or capital B, for each element of A. Letter B, if A and B are elements of this set of functions, and A and C are also elements of this function, then that means that B has to be equal to C. Okay, which means that F is single. Let me make that in a different color. Single value. Okay, so going back to your linear algebra, if we want to represent a graph that is single value, that can be easily done. Like a single value function, we can create a two-dimensional space, right? And we can define a function. So let's call this the function f. Then this is going to be A, our domain, and this is going to be B, which is our range, or y, x and y. And we know this function is going to be equal to y, which is equal to f of x, or a function of x. And we know that A and B are going to be part of this set functions. So a single value function means that if you have A here, then there's going to be a single value of B that is going to be the y value for A, which is the range value for A. And that will be true for any element in this function. So if you choose a value for A, there will be a value of B for each element of the range. So if you pick a value in the domain, then that's going to be mapped to a range value in Y. So this is a single value function. So single value f. An example of a function that is not single value is the following. Okay, so again we have a two-dimensional space here with x and y, and this is our domain, and this is our range. Okay, so one example of a function that is not single value could be a function like this, which is a step function. So for this case, if you map, let's say, a value of A here and here, when you map those, those two values will have the same value for the range of the function. So in this case we have this is not single value function. Okay, so for a function f from A to B is a relation such that satisfies these two conditions. Okay, in this case, in these two examples, this is a single value function that is satisfying these conditions, so that is a relation. However, in this case, this piece of the condition is not satisfied, so we cannot say that this is a relation. Okay, because there's elements in these functions that are mapped to the same value, even though they're not single value functions. Okay, so this is a single value function, this is not a single value function. Okay, so a set of functions. So it's not just functions by themselves, so we can create a set of them. So a set of functions defined over a set of A that is not empty, with values in the set B that are also not empty, will be denoted as a function or a set of functions A and B, where that set is the set of all functions that satisfy these conditions. So the set of functions are a subset of the Cartesian product of A and B. If A is an element of this set A, then there is set B that is part of the set B. And therefore we have A and B that are part of the function set. If A and B are part of the function set and C and D are part of the function set, then that means that A is equal to C and then B is also equal to D. Okay, so functions in general, here we're going to write a little bit, so and then I'm going to ask you some questions based on an example. So a function f is called 1-to-1 or injective if A and B are part of the function set and C and B are also part of this function set, implies that A is equal to Z. Number 2, a function f is called onto or subjective if and only if the range of f equals b, i.e. f is defined for every b in this set B. 3, if f is both 1-to-1 and onto then the relation f inverse is single value and maps every element of B onto some element of A F inverse is therefore a function called the inverse. Okay, so you're familiar with the inverse. So function f is called one-to-one or injective if there's a and b in f and c and b are also part of f, then that implies that a is going to be equal to z. So a and c are going to be the same value. A function f is called onto or subjective if the range of f is equal to b, which means that we have a definition or a value that maps from the domain to the range for every single value of a. If f is both one-to-one and onto, then the relation f inverse is single value and maps every element of b onto some element of a. Then we call that f inverse the inverse function. So let's look at one example, and I'm going to ask you to work on this, and if you get this right, then this is going to be bonus points for your final exam. So I'm going to give you 5 points, not only for being here but also for answering this correctly. So 5 points for your final exam if you get this right. So let's say we have let A being equal to 1, 2, 3, and 4, and B being equal to A, B, C, and D. Okay, so A is your domain, B is your range. Determine if the following functions are one-to-one or onto. So determine if the following functions are one-to-one and or onto. So you're going to check each one of these functions to see if they're one-to-one and if they're also onto. So the first function is going to be f equals 1a, 2a, 3b, and 4b. The second function is g equals 1d, 2b, 3a, and 4a. And the third function, h, is 1d, 2b, 3A and 4C. Okay, so you're going to write down in a piece of paper, and you tell me if A is 1 to 1 and if A is onto. And you do the same thing for B and C. Okay, so you're going to tell me again for A is 1 to 1 or not 1 to 1, A is onto or is not onto. For B is 1 to 1 or is not 1 to 1, is onto or is not onto, and the same thing for C. Okay, so write it down in a piece of paper, and let's see if we can get this in a couple of minutes. Should be very simple, hopefully. So onto 1 to 1, again, if you go back here, is 1 to 1 if for all elements A and B in F, or I'm sorry, it is going to be 1 to 1 if you have elements A and B in F and C and B in F, then that represents that A is going to be equal to C. What that means is that for every element in set A, we're going to have only one element in set B. A function is called onto or subjective if the range of B is defined for every B in B, meaning that for every value of B, which is your range, you have a value of A. Okay? So let's see if that helps you. So I'm in a good mood today. Let's do the first one. So maybe that can give you some guidance. So for the first one, it says 1 to 1. The answer is no. Why is that? Because we have for domain value 1, it maps to A. And also domain value of 2 maps to A. So that means that you have two values in your domain, or two values in your range that are mapping to one value of your range. Okay, remember the graph? So that makes the function not 1 to 1. In order for it to be 1 to 1, you only have a value in your domain, or in your domain that maps to a single value of your range. So in this case, these two are mapping to the same value of your range, so that makes the function not 1 to 1. Okay, so let me write that down. So in other words, not 1 to 1, because the inverse of A is equal to two values, 1 and 2, and it has to be a single value. When you look at the inverse of A, you notice that there are two values that are coming back as an answer. So that doesn't make the function 1 to 1. Okay, so in order for the function to be onto, we need to make sure that for every value in your set B, which is your range, so remember, this is the graph. So this is your range, and this is your domain. You're talking about X and Y here, X and Y. So in order for it to be onto, for every value that you're defining for B, let's say this is A, this is B. Let's say you have three values in your set, 10, 8, and 7. there has to be a value corresponding to it in A. So if this is 7, if this is, let's say, let's put letters we're using, let's use C, D, A. So this is 5, this is 7, and this is 10. So for every value in your domain, in your range, there has to be a value in your domain. So for this problem, for the first one, or the first functions, we have a value for A, we have a value for B, we have a value for D, but we don't have a value for C. So that makes the function not onto, because the C is not defined as part of the domain. Okay, so this is not onto because the inverse for C is not defined, is null. So I'll give you 1 minute. Hopefully that makes sense. So let's look at the second one. Is that function 1-to-1? No, right? Why not? Because is the same case, right? For 3 and 4. So this is not 1-to-1. Is it onto? It's the same case as the first one, right? So it's not defined for C. Okay, so it's not onto. What about the last one? It is it 1-to-1? Yes. Yes. Yes, 1-to-1. What about onto? Yes. Okay, so finish up that and send me and submit your paper before the end of the lecture. So hopefully that concept is clear. Okay? So we know how to define a set of functions. We know how to define the set of the domain and the range, and we know how to classify them as 1-to-1 or onto. Okay, so we are now moving to the last piece of this lecture, which is the composition of functions. So composition, let me write that down. So composition is the mathematical property from which the composition derives its name. In systems engineering, we employ function decompositions to develop functional architectures. Mathematically, however, the composition of functions f in this set f of a and b and g in this set b c, where this a is not equal to the empty set and b is not equal to the empty set and c is not equal to the empty set, is denoted as FOG, which stands for F compose G, and is defined as FOG equals these elements A and C, for which A is part of A and C is part of C. There exists a B in B, for which A and B are part of F and B and C are part of G. Okay, so what we're trying to say here is that now we know how to define a function. So if we want to connect these functions, we can use this methodology that is called composition. So for example, if you think about an operation of your machine, let's say this is a machine, you bring a part, the part is going to be processed, and then after the process is complete, maybe there's another operation that is happening. So if we define the function, we can define a function that represents that first part of the process. Let's say, okay, I'm going to put the part into the machine, it's going to go through the first process, that's my first function. And then another function that takes that part and says, okay, on the second process, this is going to happen, and this is going to be the output. If I want to make a composition of functions, basically, I'm going to take that first function and that second function, and I'm going to make it one. That composition, basically, instead of looking at what's happening in each individual station, what's going to tell me is, if you give this input, this is the output, without telling me the details inside. I have two functions, I combine them, this is the input, if you give this input, this is the output. That's what the composition of the function is going to do. So mathematically, that's how we define that composition. So for example, let's look at one simple example. So let f being equal to this set 1, 11, 2, 12, and 3, 13. And let g being equal to 11, 21, 12, 22, and 13, 23. So if I ask you what is this composition of function f of g, then you will see that there's a mapping between these two functions. Alright, 1, 11, 11, 21, 2, 12, 12, 22. So this number is the domain of the next function, this number is the domain of the next function, and this number is the domain of the next function. So if I want to create a composition of these two, then f of g is going to be equal to 1, 21, 2, 22, and 3, 23. Very simple. Again, we took two functions, two processes, and we combined them. So I know if I give you this input, if I give you input 1, output is 21. Even though there's a process happening inside. If I give you input number 2, then the output of this process is going to be 22. Because I'm combining the processes, I'm combining the functions. Is that clear? So I think, let's see. Yeah, I think I'm going to stop here. And yeah, so you're going to have a homework for this material that is going to be posted today, and I'm going to make these slides available, so in case you need to refer to them for to answer the questions in the homework.